Hi students, today we are going to talk about capacitors. Have you heard of the term capacitors earlier? Capacitors are very interesting devices that we'll study about in electrostatics that have many daily applications. For example, take the flash system of your camera for instance. These two plates that you see on your screen are used in the flash system of your camera. Similarly, capacitors are used in sophisticated timers. When they time all those events in the Olympics and the Asian Games, the timer they use has a capacitor in them. Capacitors are even used, in lowering and increasing the volume of your radio system or your audio system. So basically, capacitors are devices which are used in most everyday appliances, but we hardly get to see them or learn about them. So let's do so today. Capacitors. First of all, what on earth is this capacitance? To understand capacitance, consider this conducting body that you see on your screen. This one in bronze color. Now let's say that this body has an electric potential V initially. Now what will happen to this body if I keep adding a charge Q to this body? The electric potential of this body will keep on increasing, isn't it? So if I add a charge dq to this body, the potential of this body will actually become V plus dV, isn't it? An increase in charge by dq causes an increase in potential by dV in any body. And that is where the term capacitance comes in. Capacitance is the amount of charge to be added to a body to increase its potential by 1 volt. So if you take any body in the world, capacitance basically refers to the amount of charge that must be added to that body to increase its potential by 1 volt. So you can say that capacitance, which is represented by the symbol C, is simply dq by dV, the amount of charge to be added for a certain increase in potential to be obtained, isn't it? Capacitance is the intrinsic property of a substance. What this means is that it does not depend on the amount of charge being added to a body or the actual potential of a body. It depends on the body itself. If you take a sphere, it will have different capacitance. If you take a plate, it will have different capacitance. If you take an unevenly charged body made of copper, it will have different capacitance, isn't it? Capacitance, the ability of the body to increase its potential when charge is added to it, depends on the shape, size and material of the body. So let's say you have this disc that you see on your screen. When I add a charge Q to this disc, the electric potential of this body increases by 3 volts. But if I change the shape of this disc and make it something like this, in that case, adding the same charge Q to this body might actually increase the potential of this body by 5 volts. Interesting, isn't it? Capacitance determines by how much the potential of any body will increase when a charge Q is added to it. Understood? So that is the essence of capacitance that you must understand. So this also means that if the capacitance of a body is high, then a lot of charge must be added to that body to increase the potential difference of that body by a small amount. Now we had just studied that C, the capacitance, was equal to dq by dV, isn't it? We can take dV to the other side and then dq will be equal to C dV. We can then integrate this expression on both sides and say that integral dq is integral C dV. So now when there's this body here, say this one, at a potential V. In that case, when we keep on adding a charge dq to this body so that its potential becomes V plus dV and then it keeps on increasing like that, the net capacitance of the body is assumed to be constant in this process. So we generally assume that the capacitance does not change when charge is being added to the body, isn't it? After all, as we just discussed, capacity is the intrinsic property of a body, so we can assume capacitance to be constant. If capacitance is constant, then integral dq is equal to C integral dV, and that means that C is Q by V. So in general, instead of writing C equal to dq by dV, we can always say that C is Q by V. This is an expression that you must remember. There is, however, a special case when C equal to Q by V does not hold true. This happens when you're charging a soap bubble. Let's say this is a soap bubble. A soap bubble. Now when you charge a soap bubble, what happens is that as you keep on giving charge to the soap bubble, the charge increases, plus q plus dq plus q plus 2 dq and so on. But as the charge of a soap bubble increases, the mutual repulsion inside a soap bubble also increases, and this leads to the expansion of the soap bubble like this. So as you keep charging the soap bubble keeps expanding. Interesting, isn't it? But this happens. What this means is that in case of a soap bubble which is at a potential V, when you keep adding more and more charge to it, the soap bubble takes in that charge and the potential of the soap bubble increases, but the size of the soap bubble also increases. And because the size of the soap bubble increases, the capacitance of the soap bubble also increases. So you cannot add charge to a soap bubble without actually increasing its capacitance, because the size of the soap bubble is increasing. So only in the case of a soap bubble you cannot say that C is Q by V, because in that case when you say integral dQ is integral C dV, in that case you cannot take C out of the integral. That's because the capacitance also varies as you keep on adding the charge to the soap bubble. This is the special case of a soap bubble, but in general you can always say that C is Q by V. The unit of capacitance is farad. Now what is a farad exactly? A farad is simply 1 coulomb per volt. As you can see, capacitance is charge divided by potential difference. So 1 farad is 1 coulomb per volt. Generally we talk in terms of microfarads. That's because, as you already know, coulomb is a very large unit of charge, and therefore so is farad. So we have capacitors with a value of 7 microfarads, 10 microfarads and so on. Now before we study about the different types of capacitors, about how capacitors actually look like, and how to calculate the capacitance of bodies, let us study some important points which you must know before we study in detail about capacitors. Okay? So let's start off with the first important point. You see, I just told you that capacitance is Q upon V. When I said Q upon V, what was V? V was the potential with respect to which point? Was it the potential with respect to infinity? Was it the potential with respect to another part of the same body? What was V? In general, we consider two terminals in the system whose capacitance we are calculating, and then we calculate the potential difference between these two terminals, and that is the potential difference that we use to calculate capacitance. Understood? So by convention we take two terminals in the body and then calculate capacitance. This of course is true only when it is possible to take two terminals in the body. Let me give you an example. These are two parallel plates that you see on your screen. In that case, V will actually be the potential of one plate with respect to the other plate. So when I say that the capacitance of this system here is Q by V, in that case what I mean by V is the potential difference between these two plates. So the capacitance here represents the net charge that must be added to this two plate system to create a potential difference V between these two plates. Understood? Similarly, you can consider a spherical shell and another spherical shell surrounding it. Now if the potential difference between these two spherical shells is V, in that case that is the V that we will use in the formula for capacitance. So again, if you can say that the capacitance of this two spherical shell system is Q by V, in that case Q represents the net charge that must be given to the spherical shell system, so that the net potential difference between the two spherical shells becomes equal to V. Understood? The concept of capacitance might seem to be very new and very intriguing to you at first, but just keep on with it and I'm sure you'll definitely understand. Now what if you cannot actually consider two terminals at all in the first place? Let's say you have a sphere like this. Now where are the two terminals in the sphere? In this case, the potential V refers to the potential of this sphere with respect to infinity. So basically the second terminal is taken to be at infinity in case of isolated objects. So if the capacitance of this sphere here is C, in that case C is Q by V, where Q is the amount of charge that must be added to this particular sphere to raise its potential to V with respect to infinity. Understood? So that was the first point related to capacitance that you had to understand. The relevance of the potential V. The second point that I'm going to talk about is not exactly related to capacitance, but it must be understood by you for future concept clearance. You see, it's basically about what happens when you join two bodies with different potentials. So let's try to understand what happens when two bodies with different potential are connected together, because this concept is important to understand more about capacitors in this chapter. So let's say we have this body which has a potential V1 and another body which has a potential V2, and now I've connected both these bodies with a conducting wire like this. Now what you must remember is that when we do this, charge will be transferred from the body having a higher potential to the body having a lower potential until the net potentials of both the bodies are the same. So as you can see, this charge is being transferred from the body at a potential V1 to the body at a potential V2, and now both these bodies have the same potential V. So this will always happen when you connect any two bodies at different potentials with a conducting wire. Now a strange thing happens when we have a very large body and a very small body, and this large body and this small body are connected with a conducting wire. What happens in this case is they both still come to a common potential V, but in this case the common potential of both the bodies is approximately equal to the potential of the larger body. Did you get what I said? When there are two bodies and one of them is really large compared to the other body, in that case the net final potential of both the bodies becomes equal to the larger body. So in this case the potential of both the bodies after some time will become V1. Understood? Now this is a very interesting phenomenon. You can even derive this phenomenon by actually calculating the potential at the surface of the larger body because of both the bodies, and calculating the potential at the surface of the smaller body because of both the bodies, and equating the potentials. But for now, take it for granted that when you have a very large body in size and a very small body in size, the final potential of both the bodies becomes equal to the potential of the larger body. Now this is the concept that we'll really use in our study of capacitors. The Earth is a very large body. So whenever you connect a small body to the Earth using a conducting wire, the potential of that body becomes equal to the potential of the Earth. The potential of the Earth is generally taken to be 0. And therefore the electric potential of any body connected to the Earth becomes equal to 0. 0 potential. Now this is an important fact that you must remember. If in any circuit related to capacitors or any circuit in general, you see that a body has been connected to the Earth, in that case you can take its potential to be 0. This symbol that you now see on your screen here is called the earthing symbol. This symbol is used to represent the connection of any body to the Earth. Now since, as I just said, the Earth is assumed to be at 0 potential, therefore any body which is connected to the Earth will be at 0 potential, and so this symbol always signifies 0 potential. So if you're shown a conductor like this, like this, and then if you're shown this symbol here, this one, what that means is that this conductor is at 0 potential. Understood? So those were the points that you had to know, before we studied different types of capacitors and calculated the capacitance of different bodies. Let's now proceed and study different types of capacitors. Let's first start with calculating the capacitance of an isolated sphere. So let's say there's a sphere like this, a metallic sphere. Now obviously, since this is a metallic sphere, the net charge on the sphere will be distributed on the surface. So what will be the capacitance of the sphere? How do we go about calculating it? Well, we already know that capacitance is Q by V, isn't it? So let us assume that the net charge on the sphere is Q. Now let us calculate the net potential, at the surface of the sphere with respect to infinity, because remember we had discussed that the potential we use in capacitance is the potential with respect to infinity for isolated bodies, which don't have any terminals. So in this case, all we have to do is divide Q by the potential on the surface of the sphere, isn't it? And then we'll get the capacitance of the sphere. Now the potential on the surface of the sphere is clearly 1 by 4 pi epsilon naught into Q by R, because we had already studied that the electric potential on the surface of a sphere is 1 by 4 pi epsilon naught into Q by R. Now since capacitance is Q by V, capacitance is Q divided by 1 by 4 pi epsilon naught into Q by R, and that gives us the expression of the net capacitance of an isolated sphere as 4 pi epsilon naught into R. That's a simple value, isn't it? But you must remember it. Using this formula, we can even calculate the net capacitance of the Earth. After all, the Earth is a conducting sphere. So here we go. Let's try to calculate the exact value of the capacitance of the Earth. Well, the radius of the Earth is around 6,000 kilometers. When we substitute the value of the radius as 6,000 kilometers and when we substitute the value of pi and epsilon naught here, we get the net capacitance of the Earth as 7.11 into 10 raised to minus 4 farads. That is 711 microfarads. That isn't much, is it? Well, in general, 711 microfarads is quite a large value of capacitance. But this is the capacitance of a body so large, the size of the Earth. The size of the Earth is so large. So what this tells us is that no matter how large the body is, if it is isolated, the capacitance is less. Let's now try to calculate the capacitance of a parallel plate capacitor. What is a parallel plate capacitor? Well, nothing much. It simply has two metallic plates placed in front of each other. Now we've earthed one of the metallic plates, as you can see from this symbol. What this means is that the electric potential of one of the plates is 0. And now we want to calculate the capacitance of this parallel plate capacitor. Let us also assume, that we have imparted a charge Q to this plate, the plate that is not earthed. Now we know that the capacitance of a parallel plate capacitor is clearly Q by V, where V is the potential difference between both the plates, isn't it? So let us assume that we imparted a charge Q on one of the plates, and let us try to calculate the net potential difference between both the plates. Before we do that, however, we must understand something interesting about a parallel plate capacitor. What the interesting thing is that if you impart a charge Q to one plate of the parallel plate capacitor, a charge minus Q automatically gets induced on the other plate of the parallel plate capacitor. Why does that happen? It happens because of Gauss's law. You see, let's say this is your parallel plate here and this is another plate here. Now you have imparted a charge plus Q to the plate on the left. Now let us consider a cuboidal Gaussian surface like this. One that passes through both of the plates. Something like this. Now the plates extend like this, right? So our Gaussian surface also extends like this. So it's basically a cuboidal Gaussian surface, isn't it? Now let's apply Gauss's law for this cuboidal Gaussian surface. What you will see is that net flux enclosed by this Gaussian surface is equal to Q enclosed divided by epsilon naught. Now the net flux through this surface, this surface and this surface of the cuboid will clearly be 0, isn't it? That's because the area vector for this surface is perpendicular to the direction of the electric field through this area. You see, the electric field through this area will clearly be along this direction, isn't it? After all, we know that the electric field, because of a plate of charge or a sheet of charge, is always perpendicular to the sheet of charge. So the electric field will be in this direction. So the net flux passing through this area on the top and on these sides here, this one and the opposite side, will be 0. The only flux that will not be zero will be the flux through this side and the flux through this side, isn't it? That's because both these sides of the Gaussian surface, this side here and this side here, both of these sides are parallel to the electric field, isn't it? The area vectors are parallel to the electric field vector on both these sides. So on these two sides, the net flux will not be zero. However, we already know that these two sides of the Gaussian surface pass through the parallel plates, isn't it? That is, they pass through metals, they pass through conductors. And we already know that there can exist no electric field inside a metal or inside a conductor. So what that means is that the net electric field, for these two surfaces, this one and this one, is zero. The net electric field through this area and this area is clearly zero. And therefore, we can say that, the net flux passing through this Gaussian surface is zero. And since the net flux is zero, Q enclosed must also be zero. And we know that plus Q was the charge given to this surface, isn't it? This metallic surface. So an equal and opposite charge minus Q must be induced on the surface on the right so that the net flux enclosed by these two plates becomes zero. Now I know this was a very complicated explanation, but be careful and apply Gauss's law and you'll reach the same conclusion. The final conclusion is that a charge minus Q will always be induced on the opposite side of the other plate, in the case when you add a charge plus Q on one side of one of the plates. Understood? Now let's come back to calculating the capacitance of a parallel plate capacitor. As I had just said, the net capacitance is Q by V, and we have to calculate the potential difference between both the plates. Now let's assume that the charge density on both the plates is sigma. In that case, the electric field between these two plates because of the plate on the left will be sigma by 2 epsilon naught. The electric field, between the plates because of the plate on the right will also be sigma by 2 epsilon naught. This electric field will also be towards the right. So you can see that the net electric field because of both these plates, between the plates will be sigma by epsilon naught. That is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, isn't it? So clearly the potential difference, in the region in between the plates will be integral E dot dr, isn't it? And since, the electric field is constant, we can say that the potential difference will be E into d, where d is the distance between the two plates. This is d here, isn't it? And therefore you can say that the net electric potential difference between the two plates when you give a charge plus Q to one of the plates is sigma by epsilon naught into d. Therefore the net capacitance of this parallel plate capacitor will clearly be Q, the charge that you have provided to the capacitor, divided by sigma by epsilon naught into d, isn't it? But we already know that Q is sigma A, that is charge per unit area into area of the plate. If you're assuming that A is area of one of the plates. When you substitute the value of Q as sigma A, and when you calculate the value of capacitance as sigma A divided by sigma by epsilon naught into d, you get the final value of the capacitance of a parallel plate capacitor as epsilon naught A by d. So epsilon naught A by d is the value that you must remember, the value of the capacitance of a parallel plate capacitor. Understood? Now again, I know that this might seem a bit complicated because we're studying about so many concepts at once. But go slow, play your videos slowly, and you'll slowly grasp all the concepts. We are already ready to solve an IIT JEE problem related to capacitors. Did you know that? Let's start off by solving this problem, which was asked in IIT JEE 1987. A parallel plate capacitor is charged and the charging battery is then disconnected. If the plates of the capacitor are moved further apart by means of insulating handles, A. The charge on the capacitor increases. B. The voltage across the plates increases. C. The capacitance increases. You have to tick the correct option. What do you think? What is happening in this question? Well, first of all, let's understand what the question states. Then we will look at each option individually and see which of the options is correct. So first of all, there's this capacitor which was charged using a battery. In general, we assume that the negative terminal of the battery is at 0 potential and the positive terminal of the battery is, say, at a potential V. So this battery must have imparted some charge to the capacitor, isn't it? When the charge was imparted to the capacitor, as we had just discussed, one plate of the capacitor must have a charge plus Q and the other plate of the capacitor must have a charge minus Q, isn't it? Now the battery has been disconnected. Now we slowly move the two plates of the capacitor apart from each other. When we do that, we are given three options which are related to the charge of the capacitor, the potential of the capacitor, and the capacitance of the capacitor. So let's take a look at each option. The first option A says that the charge on the capacitor increases when the two capacitor plates are moved apart. Is that true? You see, the charge on the capacitor is simply the charge on the capacitor. So this charge, on this plate here will be constant. Like, why would it change? How would it change, isn't it? Similarly, this charge here will also be constant. After all, these two plates are independent of each other, so the charge just cannot change. Moreover, the battery has been removed. What the battery was doing was, it was adding charge, to the plates of the capacitor or removing charge from the plates of the capacitor. So since the battery has been removed, and the plates are now isolated, the charge is constant. So no, the charge on the capacitor does not increase. Therefore, this option is wrong. Let's have a look at the second option. The voltage across the plates increases. Now we already know, in fact we just derived, that the net voltage or the net potential difference between the capacitor plates is sigma by epsilon naught into D, isn't it? After all, we had calculated that the net electric field inside a capacitor is sigma by epsilon naught. So we had said that V is E into D, that is sigma by epsilon naught into D. Now what we can see here is that the net potential difference across the plates depends on the distance between the plates, and the greater the distance between the plates, the greater the potential difference between the plates, isn't it? And therefore, since the distance between the plates has increased, the voltage across the plates also increases, so this option is perfectly correct. What about option 3? Option C said the capacitance increases when the plates are moved apart. Now we just derived the expression for the capacitance of a parallel plate capacitor. C is epsilon naught A by D. Now since C is epsilon naught A by D, increasing the distance will decrease the value of the capacitance, isn't it? Because D in this expression is the distance between the plates. So clearly when we increase the distance between the plates, capacitance decreases, it does not increase. So this option is also wrong. So that brings us to the end of this IIT JEE problem. All this problem involved was testing the simple concepts related to a parallel plate capacitor. Let's solve yet another IIT JEE problem that will clear even more concepts. Can you see this complicated looking figure here? Yes, this is the figure for our next problem. 5 identical plates, each of area A, are arranged such that adjacent plates are at a distance d apart. The plates are connected to a source of EMF V. What is the charge on plate 1 and plate 4? Now again, immediately looking at this figure, which seems so complicated, and the statement of the problem, which is even more complicated, it is very easy to be bamboozled. But don't worry. Relax. We'll slowly understand what's happening in this problem and we'll work our way through it. Let's proceed. Well, this is exactly what is happening in the problem. Basically, a battery of voltage V has been connected to 5 of these plates like this. Now if you observe carefully, the positive end of the battery has been connected to 3 of the plates. For example, the plate number 5, plate number 3 and plate number 1, they are connected to the positive end of the battery. The zero potential end of the battery or the negative end of the battery has been connected to plate number 2 and plate number 4. Isn't it? So as you can see, plate number 1, 3 and 5 have a potential V, and plate number 2 and 4 have a potential 0 if you assume that the negative end of the battery has 0 potential. Now what this means is that plate 1 and plate 2 have a potential difference V. Plate 2 and plate 3 have a potential difference V. Plate 3 and 4 have a potential difference V. And plate 5 and plate 4 also have a potential difference V. Isn't it? Each of these plates has a potential difference V. Now, let's say, the charge on plate number 1 because of the battery, because, the battery charges each of the plates. So the net charge on plate number 1, let's say it's plus Q. In that case, the charge on plate number 2, on this surface facing plate number 1 will be minus Q. Why? After all, we had just discussed that by using Gauss's law, the charge on two plates connected to a battery becomes opposite to each other, plus Q and minus Q, isn't it? We had just discussed that when we were deriving, the capacitance because of a parallel plate capacitor. Similarly, if this charge is plus Q because of the potential V, this charge will be minus Q. And of course, the magnitude of the charge on plate 3 will be the same as the magnitude of charge on plate 1. Why? Because the potential V is the same for plate 1 and plate 3 and plate 5. Similarly, this will be plus Q, this will be minus Q, this will be plus Q, and this will be minus Q. So wherever, the electric potential of the plate is V, then, on each side of the plate, the charge will be plus Q, isn't it? And wherever the potential is 0, the charge will be minus Q. So you can even, draw a Gaussian surface like this, and verify that this is true. You see, if the battery charges one of the plates and gives it a charge plus Q, as I just said, the net flux passing through this surface will be 0, the cuboidal Gaussian surface that we considered. And since the net flux is 0, so the net charge enclosed will be 0. So the charge plus Q will be countered by an induced charge minus Q. So basically, we actually have 1, 2, 3 and 4 capacitors in this question, and all these capacitors have the same charge, plus Q, minus Q, plus Q and minus Q on each surface of the plate, isn't it? And that can give us our final answer. You see, plate number 1 will have a net charge plus Q. Plate number 2 has a charge minus Q on both the sides, so it will have a net charge minus 2Q, isn't it? Plate number 3 has a charge plus Q on both the sides, so it will have a charge plus 2Q. Plate number 4 has a charge minus Q on both the sides, so it will have a charge minus 2Q. And plate number 5 has a charge plus Q on one side, so it will have a charge plus Q. So as you can clearly see, the charge on plate number 1 is plus Q and the charge on plate number 4 is minus 2Q. Those are our answers, isn't it? But what is the value of Q? Well, we already know that the capacitance of a parallel plate capacitor is epsilon naught A by D, and therefore Q is CV or epsilon naught A by D into V, which is the potential difference because of the battery. So Q in each case can be replaced by epsilon naught A by D into V, and that is the final answer, isn't it? Now again, I'm sure that you might be finding it a bit confusing. Like you might say, why are we having this charge plus Q and minus Q, on both these plates? Or what would happen, if there were 3 more plates? Or what would happen if, the terminals of the battery were suddenly interchanged? Try to think of all these questions in your mind. Try to visualize the answers. Come on, take a piece of paper and, draw these plates on your paper. And ask yourself, what will happen if the voltage of the battery is doubled? What will happen if the polarity of the battery is interchanged? What will happen, if the battery is suddenly removed? All these questions sound complicated, but they're actually very simple, and you already know almost all the concepts needed to answer all these questions. So go ahead, Ask yourself questions and you'll soon understand more about this problem. Understood? For now, let's move on to the next concept. The next concept is the capacitance of a spherical capacitor. You see, we had just calculated the capacitance of an isolated sphere and that of a parallel plate capacitor. Now let us consider two spherical shells. There's this spherical shell inside and there's this spherical shell outside. The outside spherical shell has been earthed. That is, the net electric potential of the spherical shell on the outside is 0. The spherical shell on the inside has been given a charge plus Q. We have to calculate the net capacitance of this capacitor consisting of both these shells. How will we proceed? Well, we already know that C is Q by V. Q is already given. It's the charge given to the inner sphere. V is the potential difference between both these spherical shells, because as you can see there are two terminals, terminal 1 and terminal 2, and V is the potential difference between both these terminals, isn't it? So our main job is to now calculate the potential difference between these two spherical shells. How do we do that?